Just a couple of quick things before we get started. Display port?
I got it.
Okay, we got it. Fair enough. All these adapters, I mean, this is pretty insane. No. Okay, there we go. It's back. Only technical difficulties. Nothing related to Julia, thankfully. So, just a quick reminder. We are going to have the weather's actually looking pretty okay today. So we will have the group photo in the area which is usually referred to as the quad, straight in front of this nice main UCL building, the Wilkins building. This will be just at the beginning of the lunch break. So just gather, well, roughly outside of the Roberts building, you know, the main entrance where you registered, and we'll walk you over there. It's a little bit tricky. Yeah. You can get lost here. It's not as bad as the starter building over at MIT, but it's still pretty bad. Do we need to be counted in, or? Oh, we're already live. Oh, blimey. Hello, internet. Right. So I think Alan, you'll do the introduction. This is something very special. We've never done anything of the kind before. I mean, in the UK, I think we refer to this as a fireside chat. There is no fire, but there will be some chatting. So, Alan, please do the honors.
I don't need the microphone, is that right? I don't need the microphone.
Does he need a microphone?
Testing.
Okay, if you want to be heard in the room, you're loud enough. I mean, we're both loud enough.
So, as Francis said, yes, whatever he's going to say, and that many of you will also.
I won't pay any attention to the question.
That's and hopefully all of you don't have to wait till the end. Maybe nobody ever waits till the end anyway in this group, but we don't have to wait till the end to ask questions. So to introduce Gil Strang, I'm not sure Gil needs any introduction with almost 3 million views. Maybe you can log in and we can get it up close to 3 million right now. We're a little bit short, you see. But with 3 million views on the website, I think everybody in the world knows Gil Strang for at the very least, the linear algebra lectures. I have to say that I just did something on YouTube about a month ago. I was very excited. I saw it go up to 2,000 hits. I thought that was amazing for math. And then I see the 3 million, and it's like, long ways to go. So the wonderful thing, of course, about these OCW lectures is that's MIT speak for online courseware. The wonderful thing about these lectures is how it's reached linear algebra in just remote parts of the world. There have been so many amazing stories. Maybe Gil will tell us some of them. Gil is of course, a professor at MIT. I first met Gil 33 years ago, can you believe it? And I was a first-year graduate student, and I heard that there was this guy who liked linear algebra, who I should work a little bit with. So, and I've got a few other tabs to kind of just show a few other aspects of Gil. Gil, like our yesterday's keynote speaker, Nick Hyam, was a past SIAM president. Nick, of course, is a current SIAM president. You've all heard of Anna and the King of Siam. Well, this is going to be Julia and the King of Siam today. Let's see what other things I can show you. This is from the Julia paper, but was shamelessly stolen from Gil's website. This is Gil's favorite matrix. If you go type of this matrix, you'll get cupcakes. This is in cupcake format. There's the actual Julia code that produces.
So those are 2's on the diagonal and -1 on the 2 diagonals next to it, I guess.
They've already executed the code. They see that.
It's invertible, so
you can do backslash. That's right. This isn't by far the first of the conversations with with Gil, just to point out, Nick was kind enough to tell me about a conversation that went back to Singapore some years back, and I think that there was another question and answer with Gil. You remember these? And maybe the last tab I'll bring up, and I'm hoping that Gil might tell us a little bit about it. This is his latest book and class that I helped a little bit and got to see many students enjoying this class, linear algebra and learning from data, and I'll just perhaps scroll to the, there's a nice neural network, and I'll scroll to the table of contents, and then maybe invite Gil to come and have a seat right here. Maybe it would make sense to start and ask you about your latest project. Would that make sense?
Okay. The latest being this guy?
Well, whatever you'd like to say.
Right. I was going to say something about the 1806. You mentioned the 3 million or whatever, but
2 million?
but I was told the meaning of those ones on the right-hand side. So I want to know, who are those 324 people? Anyway. Yeah.
They were looking for blocked websites that were
Right,
disappointed.
yeah.
Yes. I assure you, they would download kittens.
And it was like fun to do, yeah, and yeah. So,
Would you like to talk about your latest
about
project?
what would you like me to talk about? The new book? Yes.
Yeah.
So 2 years ago, Alan's student Raj Rao, who teaches at Michigan now and has a successful course about computational thinking, really, had a sabbatical, and he offered to come to MIT and start a course. So Raj Rao and Alan and I sort of co-taught a course where students actually brought laptops to class and used Julia through the semester. Well, right, and
I can mention that I remember Raj started out thinking of using some other language.
that's right. But
quickly
he converted.
quickly
That's right.
converted.
Yeah. So it was a lot of fun. Well, it was fun doing it with Alan and Raj. So then, and a lot of students signed up right away. So we continued the course. So I taught it this spring, and actually it got videotaped this past spring, and will be on OpenCourseWare in a couple of months, I think.
Do we know it's not there yet?
I don't think it's there yet. No, you now have to. Well, of course they take editing, but the law in the U.S. requires subtitles, so that takes some time to prepare. And then I sort of thought, well, this is exciting. So it's a mixture of linear algebra and now deep learning. I'll say now and again that I'm so lucky that the subject of linear algebra, which when I took it and began to teach it, actually John Nash almost taught a section of 1806 at MIT, way back. But I was going to say, it's just so lucky that that linear algebra has just exploded in importance, as everybody here would probably know. Yeah. So a lot of departments of mathematics, a lot of professors aren't aware that linear algebra is now the right thing to know. Yeah, well, and this is just, whatever I say is like my opinion, right?
I thought this was fact.
Yeah, that's what, I've said it so often it became a fact, yeah. Anyway, it's just, so having made these videos without any idea what would become of them, then linear algebra just has taken off.
So-
And, yeah.
Oh, sorry.
no.
So it wasn't the intent for them to go live and become this big when you originally. conceived the
No,
project?
actually, I did it a few months before OpenCourseWare started. And my whole idea was, there were some fantastic lectures in the MIT math department. A guy named Rota, who was a beginner of combinatorics, sort of very early, Giancarlo Rota. He was a super lecturer. And I thought, okay, I'll set an example. And, just show these, and then get them to do it. But then OpenCourseWare started right up, and it was just natural to move the videos to that website. Yeah. So,
Gil, might you mention anything? You watched linear algebra being used in computational math from the very beginning. Do you want to say some words about how you've seen it evolve? Do people still not know linear algebra is fundamental as the situation improved?
a lot of faculty don't know, but students are seeing it. Yeah, and really the fun, one thing that makes linear algebra special is that you can do computations. With calculus, well, the answer is always 2 pi anyway, or 0. Yeah. So, but in linear algebra, it's just a natural part of teaching. Is this you probably begin with solving linear system and LU and so on, and really LU was not part of recognizing that factorizations were the beautiful way to describe linear algebra was not widely known. Yeah.
So of course now factorizations are built into Julia as a main part of our
Sure,
linear algebra.
sure.
So speaking of computations in linear algebra, I think in the elementary schools the long division debate is over, and hand calculation has lost and calculators have won. What about thinking of the analogous question in linear algebra courses, what's the balance between hand computation? Should students multiply matrices and do LU by hand, or should it be done all in Julia or some machine?
Well,
What's the right balance?
and so much depends on the professor. So many. I'm sorry to see that in a lot of universities, well, if linear algebra is a large course, which it now often is, that means it's taught by TAs, and sort of it's not in many places. So it doesn't get a professional sort of, to see what linear algebra can really be. I don't know if you remember so 2 years ago, 1806 had the different people teach it. So a topologist taught it. Well, so he took the syllabus and knocked out every application, least squares, the whole list, and added in morphisms and anyway. So it's still a struggle. This is in math departments, a computer science department, of course.
My recollection was the department never let him teach the course again.
Well, I may have had something to do with that. Yeah, well, anyway, he was a good teacher, excellent teacher, but just, so was I supposed to say something about the new course?
Right.
Yeah.
Let's put the table of contents back up, perhaps,
Okay.
or whatever you would like.
Yeah, so it begins with linear algebra, topics that we know, but sort of constructive linear algebra. I'm still writing some of it, but it's so like 1.12, right there, tensors and non-negative matrices. How many of you have like worked with tensors or so that needs to be that's a topic that hasn't made it into general linear algebra courses. And if you keep going a little bit, so then randomized linear algebra. So we all know now that if the matrix is like size 10 to the fifth, computing the SVD by a regular method is probably not the way to go, but randomized linear algebra will do it. So that's a topic that.
Are you saying that not everybody knows how important random matrix theory is?
Well, it's just always a constant effort to tell people. And then low rank topics like compressed sensing. But if you move on, so for me, machine learning, deep learning is a mixture of linear algebra mostly, and then
Where would you like to?
well, optimization, probability and statistics would be the second thing, and then optimization. So those last topics, gradient descent and stochastic gradient descent, that's key. Am I saying what everybody knows, that the algorithms of stochastic gradient descent are the workhorse of learning, and actually there's still debate about it. Do you know about adaptive methods, Adam and other guys in deep learning? So Ben Recht is really a superstar in my opinion in Berkeley, and he published a paper that that Adam, the family of methods, which people like because they speed up the convergence at the start. But he says that if you wait and wait till it converges, it doesn't converge to a good solution. The big question is, so if you have so many parameters, you often have many possible solutions to converge to. Why does stochastic gradient descent converge to a good one? One that you can then use on test data, and it's successful. That's really a deep question and hard to get your hands on when, most math proofs, if you prove convergence, okay, you've done it. But here we want to know, does it converge to a set of weights that generalizes well to new data? And the answer with stochastic gradient descent, thank God, is yes, it does. And so anyway, the question was whether Adam and related methods always preserve that good generalization. And now it looks like probably with some tweaks we're okay, but the standard Adam method could go wrong. Yeah.
So does those proofs actually rigorous, or?
Yeah, well, they construct examples, fairly realistic examples where they can do it and see what limit is chosen with different methods, and so you got the wrong one in the papers by Recht and others. So it's an amazing subject. Yeah.
So speaking of optimization, and for sure, the recent developments and popularity of machine learning has certainly become the killer app for optimization. Of course, optimization's a much bigger, has many more applications, even beyond machine learning. We have Juan Pablo Bielma here, our colleague at MIT, who's helped build the JUMP, the JUMP tool set that's become very popular in business schools and so forth. It's really brought optimization to a new level. And I wanted to ask you, you've been involved a lot with physical modeling, and I've learned so much in this Julia world. I've learned that, in the old days, getting a physical model just to work was sort of exciting enough. But I'm hearing that now that's yesterday's news, and now people are surrounding this with optimization, but they're getting stuck by the software.
I see.
Until Julia and Jump came along.
Right.
But do you have any thoughts about how optimization around physical models is changing?
Well,
everything?
actually, so I always visit Oxford in the summer for a month or so. It's just a great place to move from one office to another office, but it's a different office. And I have a bus pass in Oxford, so I go everywhere in Oxford. But I got in a conversation with some of the applied math people there. And so really the question is, how does machine learning connect to, deep learning connect to differential physical principles? Right now they're kind of two different worlds, would you say? That with deep learning you use stochastic gradient descent to find an answer. And with physical principles, you use the principle. It leads to differential equations, and we have numerical methods to solve those. And that's another big world, scientific world. But are there problems, and I think there are, in which you want to do physical problems, physical things, but that there's a sort of a very random aspect to the context, and so there'd be the opening for deep learning for gradient descent and optimization to play a part. I don't know if you have any thoughts about that. I mean, I've read a few suggestions, and papers are beginning to appear, like, could you take the learning function that's created by gradient descent, could you use that function, very complicated function, but it's, well, many parameters in that learning function, but it's built out of, layers of simple structure, matrix multiplications followed by the ReLU nonlinear thing. Could you use those functions as in the finite element method? Could you approximate the solution to a physical problem by creating trial functions of this totally new kind? Very many variable functions, but with a special neural net structure. Anyway, I don't know.
Are you saying that nonlinear algebra might
well,
maybe
yeah, that's the trouble.
play a role
Yeah.
in a world?
Well, that's alarming to think that we don't have a vector space. If we add these functions together, we don't necessarily get another one. So it's a question whether it just seems that if this learning is going to be important, and we know that physical laws and the PDs that they lead are fundamental, are the two going to meet, and how? Yeah.
There are applications, people in turbulence do.
Turbulence would be a natural,
People-
right?
Yeah.
Yeah.
So there's a recent physical review letter on Kermode-Szyszynski equation and using machine learning
Right.
to try to predict.
So
Yeah.
should we hand over the microphone? Otherwise,
Oh.
it won't be picked up by the.
Oh,
might wanna just
but we can
repeat
just
your-
repeat that
I mean,
turbulence is a great example, yeah, where it's happening, yeah, right, yeah.
I think, I don't know if Chris Rakakis is in the room, but I probably we should say that Chris is ready to give you a whole keynote speech.
Oh,
On the
okay.
subject.
Well, that's good, yeah.
So, talking a little bit about technology, so it's, I guess, undeniable that technology has had some sort of impact on teaching throughout the years.
Yes.
Would you say, what are some notable successes, some notable failures, for example, that you've seen in trying to apply technology in teaching complicated subjects?
Yeah, well, when you wrote to me before the meeting, you mentioned, for example, online courses.
Yeah, like there was an attempt, at least. I think this is an anecdote from one of my old teachers, that back in, I think it was 70s or 80s in Sweden, they had this idea that they would record the best lecturers of the land on videotape, and then you wouldn't need lecturers anymore. You could just roll in the telly.
I see,
And
yeah.
plug in videotape. But this was
This is pre-YouTube, I imagine.
this is pre-YouTube.
Maybe that's the answer to your question. It's
And
pre-YouTube.
this was apparently a horrible failure because it missed the human aspect of teaching as well.
Yeah, yeah.
So
I don't know, so I've only done human lectures.
yeah.
3 million online hits.
It's pretty-
3 million hits. That's fair.
yeah. It's crazy. One of the odd experiences was getting off of a tram in Istanbul. And as I got off, somebody said, "Thanks for the lectures." And what a world. Anyway, yeah. So,
So is that so what are the most unusual places you've seen essentially people drawing upon your linear algebra classes? Like
yeah.
some odd field, some school that you never expected, or?
it's just been a happy experience altogether, I think. Of course, one doesn't really know who's watching them or why or how useful they'll be, but it's
Well, you do know 2,944,000 people
well,
have at least gone
I
to the...
certainly never anticipated such a thing. Yeah.
But following up on the question of human learning, I think that Pontus has a good question here. You know, I sometimes wonder, maybe there's no right answer, but you build these lectures and you access 3 million people, and the students at MIT stay at home in their dorm rooms and watch. They don't come
Yeah.
to lecture.
That's
Is that
true.
a good thing, a bad thing, or is it just, it's good that the students have a choice?
I'm sure nobody here ever did this, stay home and use.
I gotta tell the truth. Yesterday,
Yeah.
I found a nice couch and I was watching these lectures.
Okay.
So, I'm now shamed, but okay.
Yeah.
Good. I'm sorry, Gil.
Yeah. No, it is a question. So MIT courses, I'm sure when you teach 1806, probably less than half of the registered students are there on a typical day.
That's right.
So that's a
Only when I
drawback.
announce what's going to be on the exams.
Yeah,
on the
that's
first day.
right. Yeah.
So they all
yeah.
come.
No, that's right. But with deep learning, they're there. That's sort of like maybe newer and kind of unpredictable. So it's still an adventure.
So you mean that there's essentially a belief among the students that maybe they can't look at last year's material because maybe the field has moved
Yeah,
and you will
it
cover
has
it.
moved. That's right. That's right. Yeah, yeah. And,
Would you like to say something about your career in writing textbooks? I've been trying to write a book for 30 years. I've sort of almost given up. You seem to do one every week. How do you do it?
every week. God, no.
I just imagine you sort of getting on the plane with an empty pad
Yeah.
and off the plane with the full book. How do you do it?
I get up early, and I write early morning usually, and after maybe like 7 o'clock to 10 or 11, and then I'm pretty washed out.
You mean you don't read Slack, check on the latest issues?
Yeah, not that time, not at that time. Yeah, so it's and you have to like it. Yeah, I sort of enjoy trying to. It's like writing a novel. You really don't know what the structure is, and I'm still changing the table of contents. I just realized that there has to be a full section of the new book on convolutional nets. So, because they're such a successful structure among neural nets, the convolutional ones are local and fewer parameters and really successful. So as I say, I didn't know. I recently reversed 2 chapters of the new book. It's I don't know how it's going to come out. this business that I mentioned of the atom type accelerations is happening now. So, you know, if I get in a conversation about neural nets, it's going to be in the book the next day. It's just.
Anybody want to?
Well, I'm sure that you could put me straight on all kinds of things. I just have a lot of people to thank for being willing to explain some topics.
So have you ever failed to finish a book in that case? Or have all of them actually been successes?
Oh, not all successes, for sure.
I think the first question is, have they all been finished?
They've
I'm
all
intrigued by
been
that question
finished,
alone.
yeah. Well, my very first book, it was about finite elements. Has anybody heard of that stuff? Yeah. So I wrote, but the only book that was never published was book 0. It was about the finite element method, but it was very mathy. It was about the finite element method on a regular grid where Fourier methods took over. Regular grid, constant coefficients, that's the context for using.
Is this the London Eye?
No.
Oh, no.
It's just more than one.
Yeah,
Okay.
yeah. It's in Zurich, what's that? Yeah, so that's the book that finally I learned that it wasn't all constant coefficients, equally spaced meshes, that the whole point of the finite element method was that it was so adaptable to a curved region. And so that's the book that finally came. And I met, that changed my life, because I met many engineers, finite element engineers. I don't know if you know any of the names from that. Zinkowitz was in Wales, and he had doesn't sound like a Welsh name to me, Zinkowitz, but he had the major engineering book, and that was just, it was exciting to meet, because I had a pretty, I don't know how you were educated, but
I learned from a professor named Gilbert Strang.
I didn't say if, I said how. But when I was a math major at MIT, it was a pure math course. I had an algebraist who came in and wrote every theorem perfectly on the board, and there were no numbers involved. And, anyway.
Does everything have to be proved in a math course?
I don't think so. And
Does anything have to be proved?
well, yeah. I have a new proof, and it's on page 4 of the new book. Now that you mentioned proofs, am I allowed to say one thing about proofs? So the first sort of like not so obvious fact in linear algebra is that the number of independent columns equals the number of independent rows. The row rank and the column rank are the same for a matrix. That's not, that's not, if you have a big matrix, that's not something you could see. Anyway, I'm sort of happy with the new twist. And then maybe I could say, can I say a little about the math of factorizations now, even the SVD. So a big favorite is if you're trying to factor a matrix A into a B times C, maybe non-negative factorization, maybe some other factorization, is how do you find B and C? So the natural algorithm is make a guess at B and find the best C. That'll be a linear problem because C is the only unknown, that matrix. Then take that C and find the best B. So alternating between B and C to always every step is get close to A in the natural norm. That algorithm, which is just like everywhere, is not yet mathematically understood. I don't think its convergence is at all guaranteed. But when does it converge? What's the, so that's a topic, you could say that's pure question, like when does this thing converge? Where maybe in a practical problem you would just do it and see. But it's interesting that a key idea, key numerical algorithm, we don't know, we don't have a good understanding of when it works. Whatever.
Let me ask Pontus I want to work my way backwards from the end. I didn't get the time check. When is the end of this?
When is the end of this? 9:35, but we should definitely leave some
Okay.
time for the audience
Oh,
to weigh
yeah,
in as well.
let's do. Yeah.
Okay, so.
There's a lot of excitement here.
We gotta get
yeah.
the mic.
Do we have a volunteer that can bring out the mics? Thank
Yeah,
you.
one here.
And I'd like to save 1 minute at the very, very end for a last question.
That sounds
Okay.
good.
We all have a burning question.
Okay.
How much have you used Julia, and what do you think of it?
I'll tell you. The truth. Do you want the truth?
Hit enter before you talk. Come on, Gil, do it.
Yeah, well, I have used it, yes. No, I remember, well, okay. I tried to use it earlier. On Julia Box, is it? It says, it suggested, anyway, when I looked, it suggested, well, just try 1 + 1 and, see 2 appear. Well, I did 1 + 1 and pressed enter, and 2 didn't appear. And right?
Shift plus enter.
It's shift enter. So how was I to know? So that's my take. I mean, like, I bought a rail ticket here from Oxford here yesterday, and the Great Western Railway said fine, I paid for it, and it was the wrong train. So this is my experience. So like anyway, I'm old enough to say, okay, just like what you do what you can, and my part is really writing and lecturing.
But Julia's in good company, because there are other bits of software that are 20, 30 years old that you also have never
Oh,
touched.
yeah, oh, right, yes.
We have a question here.
Yeah,
So you mentioned Professor Nash almost lecturing at 1306.
Yes.
And I noticed a chapter in your book about game theory. Could you comment on what linear algebra would play as a role for game theory, which is still pretty much in the wide land for lots of stuff?
I see, okay. Well, and to finish the story a little bit on Nash, so he was at MIT, and he had those were very tough years for him. Things were going downhill, and so that he never actually taught the linear algebra course that we had planned. But then, of course, we know he made a miraculous recovery and had many good years. Yeah. So, actually, I'm not in game theory, so I use two-person zero-sum games because that's a beautiful matrix theorem that von Neumann proved and Danzig and others. So for me, that's been an example, two-person zero-sum games, but not, I mean, the real thing that Nash did was n-person games, and that's infinitely harder, yeah.
Hello.
Hi.
So it's been a long time since I did pure linear algebra, like those with operators and things. So in your opinion, how important is it to know those?
To know pure linear algebra.
Yeah, so like to prove everything.
Yeah, I'm not a crazy person on proofs, actually. But to understand what like a vector space, to see the basic ideas. Yeah, I would, so for example now, my first lecture would tend to be, how do you multiply two matrices? Because I always want the class to start, you know, the new class that starts up in September. It's good to start with something that they think they know, how to multiply A times B, multiply two matrices, and then show them a different way to do it. So, and a useful way. And so in that particular case, I think multiplying two matrices, you're best to do a column of A times a row of B. Column of A times a row of B, that gives you a rank 1 matrix, a very simple matrix, and then column 2 times row 2, column 3 times row 3, and add those. So I don't know what the efficient way is
To teach or to multiply matrices?
Well, either one.
Multiplying matrices is a long, intimate story between computer architecture
Yes,
and
right,
algorithm.
it must be.
But,
Can it be told, or it's?
It's involved, I guess
Yeah.
is the word we usually
what I usually tell students is, I think you all believe that computers were invented for Facebook and email,
Yeah.
but in fact, they're actually particularly built for multiplying matrices.
Oh.
Because that is the one operation that is particularly efficient, more than almost any other
Really?
on computers, and I tell them that in an early lecture.
I see, okay. Yeah, I should take Alan's class.
You'll keep me honest the whole semester.
Yeah. Any others?
So I have a question about matrices again. But you've seen more than a few matrices in your day, probably. And what Julia has been really allowing us to do is specialize on a lot of matrix structures. Right? We know something more about the matrix and we can use something about it. But surprisingly, the way that modern programming is, or modern computational science is making use of it is actually very basic. We say like, oh, it's either, you know, dense, or it's like banded, maybe block banded, or it's completely sparse. But there has to be something in the middle, right? I'm kind of wondering, are there any kind of, you know, through all the different things that you've done throughout mathematics, do you see some kind of patterns that, you know, you're like, oh, maybe we should computationally be thinking about how we can use these kind of patterns? Is there anything that we're kind of missing from there?
It's interesting to know what's on the list of useful patterns. Now, let me just ask, so in deep learning, convolutional nets are really, they're really good because they achieve, they stay local, they look for local properties. So by a convolution, I mean the same thing as a filter in signal processing, a Toeplitz matrix in mathematics, the diagonals of the matrix are constant, right? Now so Alan would know more than I, mathematically that's a structure that you want to take advantage of because you understand those matrices. But computationally, does it pay to use that, or?
Well, I think all of applied mathematics is about using structure, as
Right,
I think I learned from you, Gil.
Yes, right, right.
That's the other thing that if you haven't seen, well, if you watch his lectures, you know, but Gil has this amazing ability to play dumb and have the student figure it out.
It pays off.
You just saw that in action, of course. I've known Gil long enough to recognize it. But there is a real point, I think, to Chris's question.
That's a very
Is it
good
possible
point.
that the word sparse is now famous and the word structured is not getting the same? It deserves more fame than the word sparse even.
Exactly. So I was taking, Toeplitz, constant diagonals as an example of a very clear structure.
And yet it's not sparse.
No, it's not sparse. And does it?
But it's more.
Does it pay to use that numeric? I mean,
of course it does.
It does. Yeah.
I have a question. Maybe a little difficult one, but you can guess. One of the biggest topics in complexity theory is the complexity of multiplying matrices. So what is your guess? Is it cubed or 2, the exponent is 2, 2 plus epsilon or greater than that. Now it's about 2.3 something, I guess.
Everybody knows that question. If you're multiplying two n by n matrices, the obvious way is n cubed steps, but it turned out to be not too difficult to find a way to reduce that exponent from 3 to 2.6 or 2.7, and now it's down a bit lower. But it's sort of stuck at, right, at the present position, where I don't have any insight here. I'm like everybody, I think. It's hard to imagine that there's some magic stopping point before 2 plus epsilon, but a lot of complexity people have worked hard on that problem. So I'm just 2 plus, that would be my guess, but we'll see, yeah. But am I right that nothing has happened to that exponent in a little while? Yeah, yeah.
Professor, now, what does the future of...
Oh, okay, yeah.
What does the future of applied mathematics look like from your vantage point, and where do you think we will see most of the action and advances in the next few years?
Well, you know, the happy thing is that something will happen. You know, there will be new ideas, basic new ideas that require new thinking. You might, you know, I'm sure that when we had finite differences for PDEs, everybody thought, okay, that's it. Then the finite element method comes along, due entirely to engineers. I think that's maybe the finite element example of creating these big codes to do finite elements is a really outstanding example of cooperation, international cooperation. Okay, so there's finite elements still growing, new ideas coming, but then we see development since then, finite volume, of course. So I think there will be more. There are ideas to find. And of course, I mean, Julia, seeing how you would do the computation is now the test. Yeah.
It's not only how you do the computation, but it's also what the computation can do for you.
Yeah. No, that's right. That's right.
Paraphrasing a president.
Yeah.
So I think we have time for one more question from the audience, I think, and then I have a question from my wife.
Yes. So we actually started it. We started, I think, a little bit late.
Oh,
so we can run over slides. So let's have two questions, one there and then one from Jeffrey, and
then there'll be the question.
And then then there'll be the question from your wife.
Oh.
So as someone who's written a lot of great books and has a lot of success in new pedagogical platforms, and all sorts of new pedagogical technologies are coming, you know, into play these days, what do you see for the future of the book, of a textbook, and books, and the new technologies?
I mean, for every author, that's a really serious question. Do books have a future? I guess I feel they have a present. So I'm still writing, and I'm whatever 83 or something. So I won't know the final answer, I guess. But yeah. So my attitude toward books is the same as what I think about going into a lecture. Is like, how can I make this clear? You know, how can I say it? Not trying to get every detail, but how can I say it so that the listener or the reader gets it? Yeah. So in some form, that's going to be with us forever.
As you all think about presentations for JuliaCon 2019, remember those words?
Right, yeah, make it clear, make it clear. Right.
Exactly.
That's, think who's your audience. And about this book that we started at the beginning, I brought 50 tables of contents that I'll put somewhere, but maybe online. The website that we realized you could look at is called math.mit.edu/learning from data. So that's the
Isn't
website,
it up here somewhere?
Alan's. It may not be, yeah.
Learning, so that's an email.
math.mit.edu/learning from data. That'll be the book's
That's what I saw,
website.
but maybe I-
It's
Yeah.
in the address field.
Yeah, but
It's
I
way
don't know
up.
how to make
Yeah.
that big.
Right.
I don't know how to make that visible.
Yeah, so I don't know if that, yeah.
My question is about how you started talking about the book. You mentioned that with stochastic gradient descent, there was some lack of deep understanding. And I wondered, to whatever extent you don't have that lack, if you would share it with us.
No, I mentioned Ben Recht, R-E-C-H-T, everything goes onto archive, and so it's all to be seen. Yeah, I'm just learning as I go here. So one of my thoughts is, make it possible for math departments to teach a course about this. And I think there has to be a book that sort of is manageable for math faculty who are not experts, and I'm not. It's such an exciting field, and you can see the structure that's just developing. It's developing as we speak to find the best family of functions, easily constructed, successful in approximation. I'm just learning.
I pontificated in the computer science department that doing machine learning without linear algebra is like doing physics without calculus. Sure, people do it.
Yeah.
But,
Right.
but.
Yeah. But probability and statistics now have a bigger role. Statistics is
Both have big
fundamental.
roles.
Yeah, just all. It's amazing mixture. Yeah.
Where were we in our one more question? And
I think that it is time for
Your
a very
turn.
special question.
So I mentioned before I left to my wife that I was going to have this opportunity. My wife knows Gil very well. And I said, could you think of a really good question? And my wife put into words something that I guess I've always known, but maybe not at the forefront of my consciousness. So these are really my wife's words, but I think them too. That Gil, you really have a talent for making people feel important in your presence, that you have this humility and grace that, I have to say that I think MIT professors are generally selected for the opposite. Just standing up and saying what you think, who cares what anybody else thinks? How do you do it? Have you always been like this? How do you, can we all learn from you? What's the,
I don't know.
think we can.
I don't think I have any answer there. I feel what many people must feel, that growing up, so many people helped me, so I'm just naturally going to turn around and help the next person, pay forward. So thanks to Susan for such a nice thought. And thanks to you all patiently. Thank you.